Okay, let's finish up igneous rocks with a few more concepts such as ophiolite suites, which are an important type of igneous rock group. We're going to start by answering questions from the videos that you watched that I posed in Video Rocks 6b.1. The first set of questions had to do with the video about Bowen's reaction series, among other things. And what I'm going to do is I'm just going to highlight the question and then pop the answer up. So what is the chemical composition of magmas formed from the melting of the mantle? Well, these would be very, very mafic or even ultramafic magmas, very low in silica content and high in iron and magnesium content. Why do you think these are called primitive magmas? Well, primitive magmas are those that form when a rock melts and that magma has not yet undergone any changes. It hasn't undergone something called crystal fractionation, which I'll talk about in a bit. It hasn't differentiated into other kinds of magmas. And so melting of the mantle generally produces a primitive magma. There aren't very many primitive magmas. As a primitive magma cools, what are the first two minerals to solidify? In this case, it would be the mafic minerals, olivine and calcium-rich plagioclase feldspar. Are these mafic or felsic? Well, I just told you these are mafic. As a primitive magma cools, what are the last few minerals to solidify? Now these are going to be potassium feldspar, muscovite, and quartz, and these are not mafic, but these are felsic. So remember, this is all something that you can gather by looking at Bowen's reaction series, and this particular version is from your lab, and temperature is here. The idea here is that we have a magma that's been generated from partial melting of the mantle, and we're starting to cool that magma, and at 1300 degrees, the first crystals to form are these mafic minerals, olivine and calcium plagioclase, and then maybe some augite as well. As we continue to cool the entire system, more and more minerals crystallize out until finally at the coolest temperatures, the last minerals to cool and crystallize are felsic, muscovite and quartz, and then orthoclase is what I called potassium feldspar in the previous slide. So what is crystal fractionation? Well, this is when a magma changes from a mafic to a felsic composition as it cools because mafic minerals have crystallized as it cooled and taken away iron and magnesium from the magma. So this picture is a helpful way to think about this. And this is from the video and also from your textbook. So here's the beginning of this sequence at a high temperature. We have a magma, which is shown in yellow, and then the gray is supposed to indicate maybe the bottom of a magma chamber, some solid rock. And the green indicates olivine crystals. So the magma is starting to cool, and the first minerals to actually solidify and crystallize are olivine. And remember, inside those olivine are atoms of magnesium and iron. As it continues to cool, we might get pyroxene or augite. It's the same thing, essentially, for our purposes. And that also takes magnesium and iron out of the magma. So the magma composition that's left behind is now less rich in iron and magnesium, and that's why they're kind of changing the color from yellow to this peach color. We then also start to get plagioclase that's rich in calcium crystallizing, and so now we're taking calcium out of that magma. Eventually, at this temperature, we've formed a bunch of olivine, pyroxene, and calcium-rich plagioclase, so our magma here in pink has a very different composition than it did over here, and that is crystal fractionation. We have fractionated some crystals out of this magma, and we have thus changed the magma to become more felsic, more rich in silica, because we've removed mafic atoms. The next video you watched was about how rocks melt. For this one, we're going to draw a diagram. First of all, what is the geothermal gradient? Well, this is one of those words where you can kind of break it down. Geo is earth, thermal means heat or temperature, and gradient is slope or change. So the geothermal gradient is the change in temperature as you go deeper into the earth. How does pressure change as one goes deeper into the earth? The pressure increases as you go deeper into the earth. What conditions related to rocks do the solidus and liquidus lines represent? The solidus is that temperature-pressure condition at which rocks begin to melt. The liquidus is the temperature-pressure condition at which rocks completely melt. and these occur at various depths. So let's draw this picture to make all three of these points a little bit more clear. First, draw a rectangle. And across the top, we're basically going to make a graph. We're going to put temperature from left to right in degrees centigrade. And you can put some little tick marks at the two ends of this rectangle, and we're going to call this 0 degrees centigrade and this one 3000. And then put two more tick marks in here that are approximately equally spaced and call them 1000 and 2000 degrees. Along the axis over here, essentially the y-axis, we're going to place depth. The surface of the Earth is going to be up here, and about halfway down your rectangle, place a little tick mark, and then divide those two regions one time each again. So we have 3 more tick marks, and we're going to call them 200, 400, and 600 kilometers below the surface. Pressure also increases downwards with depth, and I'm not going to worry about units. We'll just say that pressure increases downwards. So here's our graph. Now, do you know, looking at this, where the surface of the Earth would plot on this graph? Right here. Earth's surface is essentially 0 depth and 0 degrees centigrade. Well, it's a little bit higher than that, but it's essentially 0 on this plot. So now I'm going to put the geothermal gradient. What this means is, as you go into the Earth, this is the temperature at any given depth. So at 400 kilometers, the temperature is, looks like about 2000 degrees. At 600 kilometers, the temperature is, looks like about a little more than 2000 degrees. Okay, so this is the temperature as you go deeper into the Earth. This line here is the solidus. That is, again, the pressure temperature conditions at which a rock would melt. This one is the liquidus. That's the temperature pressure conditions at which the rock would completely melt. So this green region right here is where you would have both liquid and solid rock. So down here, a rock would be solid. Up here, in this region to the right of the red line, a rock would be liquid. It would be melted. And then in this green region, it would be both. So how do we melt rocks? Well, there are 3 ways. The first one I'm going to talk about is decompression melting. And this occurs at divergent plate boundaries because pressure decreases as hot asthenosphere rises. So let's put a point on our geothermal gradient. So here's a rock. Okay, this rock is at about, it looks like roughly 300 kilometers depth. And so by definition, this is its temperature, right? This is the temperature at 300 degrees depth. So it's a solid rock. Now let's remember, at divergent plate boundaries, the asthenosphere wells upward. As the 2 plates move apart from each other, material moves upward into the center of that divergent zone. And what does that do? Well, as we move this blob of rock upwards, we cross the solidus, assuming that we don't cool it down. And because we are lowering the pressure, we melt the rock. We begin to melt it. And that's called decompression melting. So that happens very commonly at mid-ocean ridges. What about something called flux melting? What is that, and where does that occur? Well, flux melting occurs at subduction zone, and it involves volatiles that lower the melting point of the asthenosphere. Volatiles are water and other kinds of gases like carbon dioxide that mix with the asthenosphere and lower the melting temperature. And so what happens is, what I've shown you here is the solidus, but it's what we call the dry solidus, as if no volatiles were involved. If we were going to add fluids, which we know are present in subduction zones, then we have what's called the wet solidus. And this green line that used to be here is now way over here. It's been changed. So the temperature pressure conditions at which a rock melts has changed, and that's called flux melting. So this rock didn't move at all in its pressure temperature space. Because of the change in its pressure temperature conditions for melting, it is now in this big green zone where it melts. So the presence of these volatiles, like water, like I said, will promote melting. The third way rocks melt is that you can simply heat them up, increase the temperature. That's probably the one that came to mind first. And so in this case, we're taking our rock and somehow we're making it hotter, and we're going to cross the solidus and start to melt it. And if we go all the way past the liquidus, we're going to completely melt it. Finally, you watched a video about partial melting. Why do rocks undergo partial melting? Well, it's because rocks are not made of just one kind of mineral. They're usually made of a variety of minerals, and they have different melting temperatures. Unlike a piece of ice, which melts at 32 degrees Fahrenheit or 0 degrees centigrade, minerals have a range of melting temperatures. So if you start to melt a rock by one of those three methods we just talked about, not everything melts at the same time. The rock partially melts. Complete this sentence. Most of the magma generated on Earth is formed below ocean ridges as the result of partial melting of the mantle. Which minerals melt at a low temperature, felsic or mafic? Well, that would be felsic. Remembering our Bowen's reaction series, we can look at this entire thing backwards. We can think about having a solid rock, and instead of having a magma that cools, we can have a rock that we heat up. And as we start to heat it and melt it, the first thing that's going to melt are these minerals down here, quartz and muscovite. So the very first thing that's going to melt are going to be the felsic minerals. What composition of magma is produced from partial melting? Rich in silica or poor in silica? The first things that are going to melt are going to be the felsic or silica-rich minerals. What compositions of rocks are formed directly from partial melting of mantle rocks? And that will be mafic rocks such as basalt and gabbro. How can granites and rhyolites form then? Well, in this case, you need a series of partial melting events. You have to partially melt intermediate composition rocks. So there need to be repeated melting events. And let me show you a diagram that might make this more clear. Now, I know this is a very busy diagram, and just bear with me here. So at the beginning, we have the asthenosphere, the ultramafic parent rock, and we partially melt it, right? And maybe we melt it by decompression. So as we partially melt it, we get silica-rich magma from the ultramafic parent. So we have a mafic magma. It's still mafic, but it's not ultramafic. And that cools and crystallizes and gives us basalt and gabbro, which are mafic rocks. If those rocks then partially melt, remember silica preferentially leaves the partially melted rocks, and maybe now we have an intermediate type of magma, which when cooled and crystallized forms a volcanic arc with andesite or diorite. Those are intermediate rocks. If we partially melt those, again, felsic material preferentially melts and leaves, and now we're going to have a felsic magma that will give us granites and rhyolites, which are felsic rocks. That was the whole point behind this picture on rock video 6b.1. We have a whole bunch of different minerals in a rock. If we partially melt it, the mafic material stays behind, and the felsic material melts and goes into the magma stage. The next thing I wanted to talk about are ophiolites real quickly, but I'm running out of time on this video, so I'm going to add it on as a little extra video right after this one, and then we'll be done with igneous rocks.